Hey everyone, welcome back to MLBox. In this video, we'll be discussing about similarity search and we'll primarily focus on Faiss library from Facebook for similarity search. So as we move through this video, we'll be talking about optimization techniques that could be applied on similarity search like IVF indexing or product quantization such that we can reduce the time taken for performing similarity search. As part of this video, we'll be going through this specific process. First, we'll be downloading the data set, transforming it into a format such that we can send it to the embedding model, and then we'll generate our embedding vectors. Once those vectors are present, we'll be indexing those vectors, and after that we'll be performing a query search on using Faiss search and get the top k relevant vector embeddings. And if you're not satisfied with the search results, or if you're not satisfied with the time taken by the search results, you can optimize it, and we'll be doing that in this video. And make sure you are staying till the end of the video because we'll continuously optimize the vector similarity search. Okay, so with that, let's jump on to the installation aspect. If you have Linux machine with CUDA enabled, then I would recommend you to go ahead with Faiss GPU. Otherwise, you can move with Faiss CPU. So once installation is done, we can go ahead with downloading the dataset and what are the corresponding packages that are required for downloading the dataset. So we'll be downloading this dataset with the help of request.get, and we'll be parsing the content with string.io, and we'll be creating our pandas data frame by the end. So here we do request.get and get the dataset, and then we parse the content and then create our pandas data frame. So let me import the packages and then download the dataset and create my data frame. Now we have totally 5 columns. We are only interested in 2 columns, which is sentence A and sentence B. So what we do is we turn those columns into list, and we combine those lists and we generate our common list for containing both sentence A and sentence B. So the total number of records or sentences are 4,802. Now this is not sufficient enough to understand how the optimization works. So what we do is we add more data by including these data sets. So here a bunch of URLs are present. We iterate through those URLs, do the same set of steps, get URL and get the data set, parse the data set. Those data sets are again added to the sentences. Okay. So this is what this whole block will do. So this is already running because it is already executed. URLs are already executed. So let me run this. So totally there are 20,470 records are present or sentences are present. Now there are some bunch of duplicate records or sentences are present. Some of them might be empty string. So we want to remove them. So what we do is we perform this specific step where we remove the duplicates and remove if a specific sentence or record is not a string. We remove that also. So once this is done, what we do is we turn this list of sentences into a data frame using this command, and then we combine the data frames using pd concatenate. So data frame is done, concatenation is done, and now this data.shape should contain around 14,000 sentences and it should have 6 columns. So yeah, that is done. Again, we are looking at the length of sentences. There are 14,504 sentences. So till now, what we have done is we have taken the data, we transformed it into a list of sentences. Now we want to turn those sentences into vector embeddings. So what we do is we take in sentence transformer library and use the specific BERT-based model for embedding, and we generate our embeddings using .encode method. And finally we see the shape of the embeddings. So this may take some time because you are first of all you are loading the model, and then you are encoding each of those 14,000 sentences. So this may take some amount of time, and since I have GPU, this may take less time. Okay, so it's already done. For 14,000 records, it took 14.3 seconds, that is 1,000 records per second. And each vector has a size of 768 dimension, each vector embeddings. Now to avoid this step again of encoding, what we can do is we can save the embeddings using numpy.save, because these embeddings that got generated are in numpy format. This is how you save the embeddings using np.save, and this is how you load the embeddings. Now we are at the end of second step. Our third step is done till now. Okay, we have done with downloading the data set, transforming the data set, and then generation of vector embedding is done. Now it comes to indexing and then searching. So indexing is quite simple. First we'll start with the simple process of index flat L2, meaning we will be calculating the Euclidean distance between your query vector and the vectors loaded into the index. The process is quite simple and accurate, but it is not fast. Why? So consider this three-dimensional vector. Here you have these 4 pink points. Okay, and this is xq is your input query vector. Now you want to calculate the distance between this query vector with all the vectors in your index. Now it has to calculate 4 times because there are 4 y's present. Now, if there are 14,000 records are present or 14,000 sentences are present, you have to calculate around 14,000 Euclidean distances. Now that may take some time. Okay, so that's why this is simple and accurate, but it is not fast. Anyway, what we'll do is we'll implement this and then we'll go ahead and optimize this similarity search that we are doing. We'll try to optimize that. So first we import Faiss, and then what we do is we get the size of the embeddings, which is 768 dimension, which we know already. And we see, since this is plain and simple indexing, it is already trained. Okay, so you don't have to train the model or train the index of Faiss. So the index is trained already, and in the next step, as we optimize, we might have to train the index based on certain criteria. Okay, now the index is trained. Now we want to add our vector embeddings to the indexes. So what we do is index.add, we do our sentence embeddings. We are passing our sentence embeddings. Now it is part of your Faiss index, and we can see the number of vector embeddings that are present inside your index, so which is 14,504. Now we are done with indexing aspect of Faiss indexing, because we have already added our sentence embeddings to Faiss index. Now what you want to do is you want to search your index. Given an input query you can give, and you can search the top 4 or top 5 similar elements or top 5 similar sentences. Okay, so that we can perform now. So we want top 4, that's why we give k is equal to 4. And this is your input query, which is someone sprints with a football, and we encode that using that embedding model and generate our query vector xq. Once query vector is generated, what we do is we do index.search and pass in the query vector and pass the top 4 elements that we want to retrieve and get our d comma I. So the key point here is we have this print of I. It gives you the 4 indexes which are similar to the query vector which you passed. Now we can go ahead and see this index, what it contains, whether it is similar to what you have sent as the input. And also one more point you have to note or keep track of is the time taken for performing this activity or this search. It is around 16.3 millisecond. Now keep track of this time, because we'll be optimizing for this specific metric. Now we have this 4 indexes, and I'm just using this data frame which we had, data of sentences.iloc. Now we pass those 4 indexes and get those 4 sentences which are similar to the input query, which is football, sprint, something like running. So this, all the 4 sentences that we got are related to football, and it also contains terms like running or playing. Now this is with respect to simple and plain indexing. Now what we want to do is we want to improve or optimize it. But before we do that, let's understand how we can fetch this corresponding vector embeddings. To do that, what you can do is you can create a dummy vector first of zeros of 4, 768, Since we are like looking the top 4, that's why we give the k is equal to 4 comma d, which is 768. And these 4 indexes that we got, 330, 6201, 1305, 0755, we iterate through those and reconstruct our embeddings, and we store it in vectors. So let me run these two. So we had 4 vectors. We are looking at the first vector under till 100 dimensions. So these are the different values. Now why we are doing this is because we can, if you want to visualize it, you can visualize it on some using some other library if you want to visualize these embeddings. So leaving that aside, now let's talk about the speed. So we were using simple plain index flat L2, and which is computationally intensive because you had one query, 14,000 records. So you were trying to calculate the distance between these two 14,000 times you were calculating the L2 distance. Okay, so when it has like millions of records, you cannot do that. Okay, because it will become like, in terms of compute, it will be occupying a lot of your CPU. In the graph we can notice that, okay, as the number of vectors are increasing, the number of query time, right, it also increases because it has to search through all the records. It is like linear time. So to avoid that, so it also mentioned here, for millions and billions of embeddings, the index quickly becomes too slow to be useful. So we need to do something different. Now what is the different thing that we have to do? So you had like around, consider, right, you have 14,000 vector embeddings. Now what you can do is you can group them together or cluster them together based on certain similarity. Okay, and create a centroid. Like K means clustering. If you know, there will be a centroid and there will be a cluster. So for each cluster there will be one centroid. So here what we see here, right, we end up creating Voronoi cells. Okay, and each cell will contain a bunch of vector embeddings and a corresponding vector centroid. So as these points are shown here, these are the centroids and these are each cell, and each cell contains a bunch of vector embeddings. Now what we do is, this is like partitioning the index. Okay, so when you are trying to search next time, what you will do is you will end up selecting one centroid or one cell and only a bunch of records that is present inside that cell. So by this way, we are reducing the search scope for vector search. Using this method, query vector xq identify the cell it belongs to, then uses index flat L2 or another metric, which we'll talk about later, to search between the query vector and all other vector belonging to that specific cell. So each cell contains a bunch of vector embeddings. So what we do is we just reduce the scope of the search by selecting one cell at a time. So what we do first, if you see here, the changes that you have to bring in, endList is equal to 50, and again we are initializing this quantizer for index flat L2, and then if you see here, we are using something called as Faiss index IVF, which is inverted file index flat. Then you apply this quantizer, whatever you have built here, and then D, which is the dimension of vector, which is 768, and endList is equal to 50. So the 14,000 records that we had are split into 50 clusters, and there are like each of them have their centroids. Now when you are passing your input query, that centroid from that cell will see which is closest to that specific centroid. That query vector is closest to which specific centroid, and it will go and select that specific cell. So we have created our index now, which has 50 clusters. Now, is it the index is trained? No, because we want to split it into 50 clusters. We have to train it, we have to cluster it. So to cluster that, what we have to do is we have to do index.train, and this will cluster those embeddings into 50 cells, and then you can check whether the index is trained or not. And once it is trained, you end up adding your sentence embeddings. So first you are training, and this will create your grouping or transformation, or which is basically clustering, and then you see whether it is trained or not, and then you add up your sentence embedding to index. So now the index is trained and we have our sentence embeddings inside our index, Faiss index. Now, so it is trained. I don't want to run this command. Okay, what is the total number of vector embeddings present? So 14,504. Now again what we do is, again we are searching. Again we have our vector embedding, which is the query vector embedding XQ, and the top 4 results that we want to see. Let me run this. It's the same set of indexes. Again it got searched and the time taken is 1.1 millisecond. If I go back here, if you see earlier what it took around 16.3 millisecond. Now it reduced to 1.1 millisecond, which is quite drastic change. Now let us see this sentences. I think it's the same 4 vector indices we got. So these are the 4 same sentences that we got, and we reduced the time by 16 times. So note, since I tried it earlier also, okay, at that time what happened was, it was taking around from milliseconds to microseconds earlier. Now when we ran it again, it is taking milliseconds, but it is reduced by 16 times. So what happened is, finally, as I said earlier, so the scoped search after partitioning the index. So when you are searching again using Faiss search, since we have split our indexes into 50, it took one specific cell and all the records inside that specific cell. So we reduced the search scope for our similarity search. Previously the probe was done on a single cell. Okay, now consider, right, now you have gotten your result, which is this one, which is perfect. As we done, exhaustive search was done, it was the same result that we got. But assuming this is not working fine, okay, because since we are looking into only one cell and whatever the records that are present inside that one cell. Now if the result is not good, what we can do is we can increase the scope by taking around 10 more cells or 5 more cells as you need. See if the result is better or not. So what we do here is we perform index.nprobe is equal to 10. It means that it will look into 10 cells and all the corresponding vectors inside those cells. So now if you do the search, it is around 1.98 millisecond. Again, this is also, the time taken is quite less when you compare to what the exhaustive search that we were doing at the first. And it is again giving us the same result. Since it was also perfect, the earlier one which we did with one cell, since that was also good, and this is also good, the result that we got. Now I want you to understand this specific graph also. So IVF flat 1, okay, meaning I'm looking into only one cell and all the corresponding vector inside that specific cell. And if I give IVF flat 5, I am looking into that specific number of 5 cells I am looking into and all the specific corresponding vectors. And the time taken for, as we increase the IVF flat 1 to 5, 5 to 10, 10 to 20, the query time will increase. Because if you see earlier, it is taking 1.98 millisecond, and earlier when I was doing for nprobe is equal to 1, it was giving 1.1 millisecond. So it increased by 0.88 millisecond since we changed from nprobe from 1 to 10. So this is one way of reducing the time for searching by indexing properly with IVF. Now since we have performed this IVF, there is no mapping between what original vector and the index position. So what we want to do is we can do something called as index.make direct map and then reconstruct the indexes. So this will be useful for, again, as I said earlier, if you want to go into each of those results that we got, what was the embeddings, right? Like 100 dimensions of those specific embeddings, that we can look into it. Now finally, the product quantization. So this is basically you are trying to convert your vector into subvectors, and then if I just show you this process here. So we split the sentences, or not the split the sentences, we split the original vector into several subvectors, as we can see in the image, and each of those subvectors we perform clustering. So this will create multiple centroids for each subvectors. Since we are performing clustering on the subvectors, we'll have multiple centroids for each subvectors. And in our vector of subvectors, we replace each subvector with an ID. So instead of having what I could call a vector, okay, subvector, what we do is we map those subvectors to an ID. And those IDs will be considered as our nearest set specific centroid. So we'll be mapping our vectors to some ID, and that ID will represent those similar documents or similar vector. Okay, that's the whole point. So let me just read through this one. So each index stores the vectors as full vectors, and we can compress those vectors using product quantization, and it is an additional approximation step with a similar outcome to our use of IVF, where IVF allows us to approximate by reducing the scope of our search, okay, by the, as we done earlier, like we are reducing the scope of our search by turning into clustering and then selecting the cells. Here what we do is we approximate the calculation of distance or similarity, because earlier we were calculating full vectors distances. Now what we do is we create it into subvectors, and those subvectors are again clustered, and those clustered subvectors are turned into some IDs. Now we want to identify those IDs, how they are like matching or not. So for this, how to implement this one? So number of centroid IDs in the final compressed vector that we want is 8. The number of bits in each centroid is 8. So this is like also reducing, I guess, the memory, I guess. So again what we do here is we take the index flat L2 and create our quantizer, and the index D is, the D represents the dimension of the each vector, which is 768. And what we do here is we use something called as index IVF along with PQ, product quantization, and we pass in our quantizer and pass in our dimension, and the end list is nothing but 50 was our value, end list is equal to 50. EM is our number of centroid IDs that we want, and bits is number of bits in each centroid to represent each centroid. So whether this is trained, so this is also not trained. So what we do is we pass our sentence embedding and we train the index. Now while that is happening, this is next step is to add those sentence embeddings to the index. And now interesting point again. So previously we were using index nprobe is equal to 10, and we got the time taken was 1.98 millisecond. Now since we are also performing product quantization, the optimization should be much better, and then the time taken will be reduced further. So we have done index.nprobe is equal to 10. We are taking like 10 cells we are taking in, and we are searching through those 10 cells. Now if you see the time taken now, even though there are 10 cells, instead of 1.98 millisecond, it is 1.17 millisecond. Okay, now if I do just nprobe is equal to 1 and do this indexing, okay, if I do that indexing and then I search, it took around 6.6 millisecond, or it is 657 microseconds. So it got further reduced. If I index it like 5, okay, nprobe is equal to 5, so it took 496 microseconds. Now the results part, okay, so we got our 4 indexes again here, and if you see, there are some changes now. Though we try to optimize it a lot, there is some changes we are seeing. This specific was not there, this specific sentence was not there when we are doing exhaustive search, or when nprobe was is equal to 1 without product quantization itself. Okay, this is new because since we applied too many of optimization, there are minor changes in terms of the results that we are seeing. Because if I go here, this is like 587 was not there, other rest of the index were present. Okay, if I go here somewhere, so yeah, this was present. Okay, this is not present, 6201 is missing, I guess. Now 6201 is missing, yeah, and even this one is also different, I guess. So anyway, so we moved from milliseconds to microsecond after product quantization, And by adding PQ, we have reduced our time from milliseconds to microseconds. Minor changes in results can be expected. Thus, both our speed optimization operation IVF and PQ comes at a cost of accuracy. So this is the final graph that we need to understand. Okay, the time taken is drastically reduced when we compare it to simple plain flat L2 and IVF based flat L2 and then IVF based PQ. Okay, so the time taken changes drastically. So that's the idea behind this specific library and the optimization. So clearly a lot can be done using index flat L2, index IVF flat, index IVF PQ, and each has the parameters that can be fine-tuned to our specific accuracy and speed requirement. Okay, when they say fine tune, okay, I mean by that they mean like n probe is equal to 5, 10 or 1, whatever, right? Those parameters can be fine tuned such that you can get an accurate result, and also it meets the speed requirement of your search. So we are at the end of the video. So we are done with similarity search with Faiss, and I hope you understood the whole process, how to optimize your similarity search with Faiss. So with that, I'll be concluding this video. Thank you for watching and staying till the end.